So this is an update video for systematic naming because if we look back at the previous videos, we've covered nearly everything that we need to know to systematically name all the different types of compounds featured in the topic at National 5, but we've not touched on naming alkenes using systematic naming. So if we think back to our rules that we established for systematically naming a compound, first of all, we had to find the longest carbon chain. So that was all carbons all joined on to one another continuously, so you don't need to lift your pen off of the page with no branches. And then we numbered that chain of carbons starting from what we called the most exciting end. So in previous cases, that was where there were more branches. And then we identified what those branches were by their name based on how many carbons were in them. So we could have methyl branches for one carbon, ethyl branches for two carbons, etc. And then lastly, we would come up with a name systematically based on those findings. And what I didn't mention is that we should always list any branches that are featured in alphabetical order. So for example, if I had both an ethyl branch and a methyl branch, regardless of where they appear in the chain, one could be at carbon 2, one could be at carbon 5, it could be the other way round, it doesn't matter, we always list them in alphabetical order. So ethyl would come before methyl, for example. That's very important to keep everything consistent. However, what if we wanted to name a branched alkene? Because we're then left with the dilemma of, okay, if we look at this compound here, for example, it would be quite easy to identify the longest chain. We can see, I'll just do it for quickness here, it's across the middle. We have 6 carbons all joined together. Oh, missed a bit there. So the first step is actually quite easy, and it's not changed. However, the problem now lies in determining which end is the most exciting. Our rule isn't quite comprehensive enough now, because on the right-hand side, we have some branches, 2 methyl branches, and before we said that made that the most exciting end, the side with the most going on. But now on the left-hand side, we've also got this. We have a carbon-carbon double bond in this unsaturated alkene compound, which is also quite exciting because that does things. We now know about alkenes, we know about double bonds, we know about addition reactions. We know that this bonding here can undergo some specific chemical reactions. So we have to ask ourselves, well, okay, is there an order, is there a hierarchy of determining which things are more exciting than others? And the general rule for that is if it's a functional group, then that is more exciting than branches. Branches, at the end of the day, aren't actually all that exciting. All they do is get in the way. They're just a bit bulky. It just happened to be that in alkanes, they happen to be the most exciting thing going on because alkanes don't really have anything else apart from single bonds and carbons and hydrogens. So from now on, whenever you're trying to determine what is the most exciting thing, the most chemically active thing, if you like, if it's a functional group, that takes the priority. And a carbon-to-carbon double bond counts as a functional group. It counts as something that tells us what that compound is. And we'll come on to some more functional groups in the next topic. But for just now, the one that we know is this double bond. So, in deciding which end we should name from, the most exciting end lies with wherever the double bond is. And it's also important to mention that whenever I'm choosing my longest chain, if there's a double bond, that double bond has to be included in that chain. Even if there is a longer chain elsewhere, so say for example this chain here that has 4 carbons, if that went on and on and on and extended that way to more than 6, maybe it was 7 or 8, I still couldn't use that one because it doesn't feature this double bond. So the point I'm trying to make here is if there's a double bond, it becomes the most important thing in that compound because it makes it the alkene. Without that double bond, it's not an alkene. So include it in the longest chain and make it the most exciting thing in the compound. So if we start numbering, we would in fact go from 1 to 6 from left to right because our double bond is closest to this side. And now we can start trying to name it. So we have a methyl group here and we have a methyl group here. They are joined on to carbons 4 and 5 based on how I've numbered my longest chain. So I have to write 4, 5, dash to separate my numbers and letters, dimethyl, because there are 2 methyls, and then the last part of the naming convention, we have to say that this is some form of hexene, because there's 6 carbons and there's a double bond. However, we want to be even more specific now. We want to highlight exactly where that double bond is. And we do that in the exact same way as we do with our branches. Whatever is the lowest carbon that has the double bond, wherever the double bond starts, if you like, that is the number that we are going to insert into the hexene name. And the way that we do it is we write our prefix first, in this case hex. We do a dash with the number where the double bond starts, in this case it's carbon 2. And then we show that it's an alkene by ending it in ene. So this molecule is in fact some kind of hex 2-ene, because the double bond starts on carbon 2. But it also features 1, 2 methyl groups, making it dimethyl hex 2-ene, and those methyl groups feature on carbons 4 and 5, so it's 4,5 dimethyl hex 2